Okay, so I'm going to jump into Bayes' rule a little bit. Some of this is kind of weird, but it's not too bad. So let's talk a little bit about the law of total probability. This thing is so important that it requires a law and not even a rule. The law of total probability tells me that I can find the probability of an event by taking the intersection of that event with another event plus the intersection of that event with its complement. That should be C. I forgot to make that C because So if you think about it, here's the probability of A. So if we look at where the intersection is, it's right here. So that's the probability of the intersection of A and B plus the probability of the intersection. Remember, out here is B complement. So everything that's not B is B complement. So taking the intersection of B complement and A is pretty much the rest of A, right? And then we have all of A covered. Now remember, using the multiplication rule, we then have this. The probability of A given that B occurs times the probability of B plus the probability of A given that B complement occurs times the probability of B complement. Now this is really interesting. We can use this for a lot of things and to find probabilities when we're given tables of data. And let's talk a little more about this online shopping. So 52% of the US population is women, and 32% of women shop online at least once a week. So to write this out, we can even make a contingency table about it. So we have women, we can have gender up here, and we can have online shopping at least once a week. So we have women, men, and total. So we know the probability of someone is a woman is 0.52. So the probability someone is a man, we're going to say is 0.48. Here's 1. Then we know that the probability that someone is a female that shops online, we multiply these two together, was 0.1664. So this is yes, no. 0.1664. So if this is 0.1664, what is this number? Well, remember, we can add and subtract going downward. So this one is 0.52 minus 0.1664, and we get 0.3536. So we need more information to figure out the men. So now, what if we knew that 12% of men shopped online at least once a week? Of men. So that's 12% of this 48%. So 12% of the 48%. So remember, we want, these should be complements. So we want the probability that someone shops online and they're not female. So the probability they shop online given they're not female, 0.48, times the probability they shop online, probability they're not female. Ooh, we have these backwards. That's okay. This is the probability they're not female. This is the probability they shop online given that they're not female. And we get 0.0576. This one goes here. And we can fill in this entire joint probability table using all of this information. 0.0576. So we get 0.4224. Now what we can do, what is the probability that a person selected at random shops online at least once a week? So we want to find this. What's the probability that a person shops online? And I should change this to S, and we'll say N for not shopping. But the S is when they shop online at least once a week. So all we have to do is take this number and add it to this number because we know we can add going across. So it's 0.1, well, it's 0.224. And the probability that somebody does not shop online at least once a week, well, that's 1 minus 0.224, or 1 minus 0.224 equals 0.776. So I filled in this entire contingency table just using these pieces. I filled the whole thing in. So remember, inside, these are intersections, not conditionals. You have to multiply them in order to get the intersection. So you need to find these intersections using this rule. And we have the entire contingency table made. So a probability that a person selected random shops online at least once a week is 22.4%. Probably old data. Maybe not. I don't know. I think it's a little bit old. Okay, whoa. That stuff got really small on us. Okay, so I want you guys to think about what we have, and you can't see this, so I'll write it. Mutually exclusive, exhaustive events. And that's not that you're getting exhausted from watching this video. Mutually exclusive exhaustive events are where the probabilities all add up to 1. So like the roll of a die, the mutually exclusive events are 1, 2, 3, 4, 5, 6 on a dice roll. So the probability of 1, 2, 3, 4, 5, 6, or 6 is 1, because it's 1/6 multiplied to itself 6 times. So it's 1. So we can actually generalize this law of total probability to be a sum of a bunch of things. So if I take the probability of B intersection A1, I'd get this piece, B intersection A2, B intersection A3, B intersection A4, B intersection A5, and if I add all those up together, I end up with the probability of B. Kind of cool. And that is just to take the whole thing and generalize it. So we can actually use that to do some fun things. So let's look at this. This is the percentage distribution for region of residence and percentage of seniors in each region. So looking at this, we want, what is the overall percentage of seniors in the United States? Well, this is the percent of the U.S. population who lives in the Northeast. So this is the probability somebody's from region 1. We're calling this region 1, region 2, region 3, and region 4. These are the percentage of the region that are seniors. So this is the percentage of this 18.3%. So what we essentially have is the probability that someone's a senior, given that they're from the region 1. So as you can see, if we just multiply these across, we would get the probability that someone from the Northeast was, well, the probability of someone from the U.S. is a Northeast senior, because it's 13.6 of the 13.6% of the 18.3% of the U.S. that lives in the Northeast. So we can multiply all these across. So we have 0.183 times 0.136. So this one's 0.0249. So 0.128. Oops, I didn't get the point in there. Insert decimal. Okay. Times 0.222 is 0.0284. So remember what these mean. This is if you selected someone from the United States at random, there would be about a 2.5% chance that they would be a senior citizen from the Northeast. So if I look at 0.363, a lot of people live in the South, 0.125, I would think the Northeast would be bigger, 0.045, call it 4, 0.232 times 0.112, and we get 0.026. Okay, so let's add. So now if we add up all of these, we should end up with the probability that someone selected at random from the US is a senior citizen. Because all of these are mutually exclusive, because they're all from different regions. So let me go pick up this one. Plus this one. Plus this one. And you can always go and do this the way I just did it. And we get 0.1247. So this is telling me that 12.47% of the US is seniors. And how does this help you? This means that if you have data, if you look up data on the internet and it's laid out like this, that you can get and you can kind of aggregate your data and say, oh, well, 12.47% of the population are senior citizens. So remember, these are all, say, the totals on one side of the contingency table. These are conditional probabilities. You're trying to find all of these joint probabilities, and then you can find that total. So there's a couple of interesting things using this that I kind of want to show you guys. So one of them is what we call the mysterious case of the false positives. So let's consider a rare disease which only affects 1 in 1,000 people. That is 0.000, no it's not, it's 0.001, 1 out of 1,000 people, okay? There is a test for it. That test is 99% effective. So it finds the disease 99% of the time. Oops, however, it has a 0.02 false positive rate. What is the probability that someone who tests positive actually has the disease? I want you guys to think for a second. Are you thinking high numbers? Are you thinking small numbers? I want you to kind of give yourself a guess and kind of maybe write down that guess somewhere and see how close you were. See, you're at home or you're in the library listening to this lecture, and no one's going to know if you were wrong. So you can do this however you like. So let's write this down. The probability someone has the disease. So D is that someone has the disease. It only affects 1 in 1,000 people. So the probability you have this disease is only 0.001. So the probability that you test positive, and so T is testing positive, and D is having the disease. So the probability that you test positive, given that you have the disease, is 99%, so 0.99. The probability that you test positive, given that you do not have the disease, is 0.02. Makes sense, right? So we want to find what is the probability you have the disease given that you test positive. We want to switch this guy around. And it's going to be very, very different. So let's go like this. What is the probability? Let's work from here. Well, using the conditional probability rule, that should be the probability that you have the disease and you test positive divided by the probability that you test positive. Now, neither one of these things I have. However, remember, if I take this piece, I can find this using the other way. So I can look at this one the probability of T given D times the probability of D. So I can find this piece. And that's equal to, let's see, that's 0.99 times 0.001. So what do we got? 0.99 times 0.001 is, ooh, that's pretty small. That's what I was talking about, the little e on your calculator. So we have 9.9 times 10 to the negative 4. So move this decimal place over 4 times. So we get 3 zeros, 99. So let's make our contingency table up here. So this is you have the disease, you don't have the disease, you test positive, you test negative. Let's make our totals. So we know that this total right here is 0.001. So we know that this total has to be 0.999, right? So this is 1. So what else do we know here? We just found out that intersection of D and T is 0.00099. Okay, so the probability that you have the disease and you don't, and you test negative, it's going to be pretty small. 0.001 minus this number, which is 0.1234. So that's pretty tiny. It's not very likely that you have the disease and you test negative for it. So let's look over here. So we have to figure out these ones on this side right here. So we know that the probability of T given that you don't have the disease is 0.02. So how would we find this box right here? So how would I go about finding the probability of T intersection DC? Well, I could do that by finding this, which I have, times the probability of DC, right? D complement. Well, this is 0.02. What's the probability you don't have the disease? Well, 0.999. So 0.02 times 0.999 is 0.01998. So now we found that piece. So that piece allows me to find the rest of them. So I can find this piece right here. So let's find that piece, 999 minus this number. And that's 0.97902. So now I can add these across and find these answers. So let's see what we've got. We've got 0.00099 plus 0.01998. That's going to be 0.02097. And over here, so down here, 1 minus that number is 0.97903. Okay, so now we see the probability of T, and we have the probability of T intersection D. So we have all of the pieces of this, 0.00099 divided by 0.02097, because now we're only looking at if you test positive. And let's see what that is. 0.00099 divided by, what was that one, equals, that equals 0.0472, or 4.72%. So interesting. That means that for a disease like this, you could test positive and you would only have a 5% chance of actually having the disease, less than 5% chance. Not a reason to be too scared about anything right there. So, that's an interesting one. Another one, so that kind of brings me to actually Bayes' rule, which is sort of interesting. So Bayes' rule, it's an extension of what we just did, but it's basically how we can turn around a conditional probability. So if we need to turn around a conditional probability, we can do so using this formula. So it's essentially, we're taking this and we're saying, well, probability of AK given B is equal to the probability of AK intersection B over the probability of B. Oh, but wait, I can switch that to the other way on top. And then I can use the law of total probability to find this bottom one. So let me show you what we're going to be doing with that. So this is one of my favorite things, is the Monty Hall problem. So you are on a game show called Monty Hall. So behind one door is a new car. Behind the other two are goats. And you're going to choose door number 1. Okay? So, now, Monty Hall knows where the car is. So he shows you door number 3. And he asks, would you like to switch doors? Now, this is the big question. Do you have a mathematical advantage to switching? Most people say no. Because they go, well, no, now it's 50-50. It's either one of these doors. It's a 50-50 chance. It doesn't matter if you switch or not. But I contend that it's not that way. I contend that the probability that the car is here is a 2/3 probability and the car is here is a 1/3 probability. And that is using Bayes' rule. So, let A be the event that the car is behind door 1, B be it's behind door 2, and C being it's behind door 3. Now M is that door, whoops, I should say door 3, because that's the one we opened. Door 3 was opened and revealed a goat. Well, we'll have to say 2, because the rest of this is 2. So using Bayes' rule, I want to turn around the probability that the car is behind the original door you chosen, given that he opened, say, door 2. And we want to switch that around. BM given A times the probability of A. Now, here's where it gets interesting. The probability that he opens door 2, given that the car was there, is 1/2. Because if you choose right the first time, he's going to randomly choose one of the other 2 doors. So that's 1/2 times the probability the car was there in the first place, which is 1/3. Now we divide that by, again, the same thing, plus 0, because he's not going to show you where the car is, plus 1, because if the car is behind door 3 or door, say, then he can't show you that. He's going to show you where the car isn't. So if the car was indeed behind door 3 and he showed you door 2, that's the only door he could have showed you. So the probability of M given C is 1. So we end up with 1/6 divided by 1/2, which is 1/3. And the probability of C, now we have 1 over 1/3. See, you have a whole chance. You have a 1 up here instead of a 1/2. So that comes out to 2/3. We'll talk about this a little more in class. It's kind of a fun little game to play. So we'll talk about that a little bit more. One other thing I want to mention real quick is that if I go back to this particular problem, I can actually use Bayes' rule now to find out what is the probability that someone is from region 1 given that they're a senior citizen. And I can use this information now. So I can actually go back and say, well, that is the probability that they are from region 1 and a senior citizen divided by the probability they're a senior citizen. And I already know this is 0.1247 because that's my total. I use total law of probability, and I want this portion of it, the 0.0249, which I already found. So this makes Bayes' rule, which looks really difficult, it makes it a lot easier. So we can go 0.0, whoops, turn it on, likes to turn itself off. 0.0249, whoops, forgot my 0. I didn't forget it, I pushed it. It just doesn't like to listen to me. Divided by 0.1247 is 0.1997. So this is telling us that nearly 20% of senior citizens live in the Northeast. So about 20% of senior citizens live in the Northeast, but only 13.6% of the Northeast residents are senior citizens. And that is the difference. So sorry, this one was a little longer. We'll talk about a lot of this stuff more in class. It's kind of fun, kind of interesting. So I'll see you later.